Consider the equation x square is equal to -3. If we have equation x square is equal to -3, we know that there is no real number whose square is -3. We have no any number whose square is -3.
-3.
Therefore, the solution x square is equal to -3 does not exist in the set of real number. We cannot find any solution x square in real numbers. Euler was the first mathematician who could solve such equation. For this, he developed the idea of imaginary number, and thus we got complex number system. Complex number system is given by Euler. Second article second, symbols iota and its powers. Iota and its powers. Does not exist in real number. Now value of iota is equal to square root -1. Iota square is equal to
-1.
-1 square root square is equal to -1. Iota cube, iota square into iota. -1 into iota is equal to minus iota. And iota 4, value of iota 4,
1.
is equal to iota square into iota square is equal to -1 into -1, 1. And so on. These are the values of its power. Article number 3, complex number. Any number of the form a plus iota v, suppose that is equal to a plus iota v, is called complex number. And where a and b are real numbers and a and b are real number and iota is equal to -1 is imaginary part, imaginary number.
और पढ़ दे पहले वाले वाच करना लगा देखो घंटे के बाद जो ना जाके तो पढ़ देगा
There is called real part. Real part and B is called imaginary part. Article number 4, if a complex number is 0, then its real and imaginary parts are separately 0. If we have a complex number z is 0, then a and b are separately 0. A is equal to 0 and b is equal to 0 by, because z is equal to 0 plus iota 0. Okay, if a complex number is 0, then a and b are separately 0.
0.
Article number 5. If two complex numbers are equal, then their real and imaginary parts are separately equal. If two complex numbers are equal, let z is equal to a plus iota b, and other complex number is, first is z1, second is z2, c plus iota d. If z1 is equal to z2, if z1 is equal to z2, then a is equal to c and b is equal to,
Iota b is equal to d.
only b is equal to d. Prove that the sum, article number 6, prove that the sum of the two complex number is a complex number. When we add two complex number, we will always get complex number. If z1 is equal to a plus iota b and z2 is equal to c plus iota d, and if we add z1 plus z2, we will get a plus c, b plus d iota, which is a complex number. Article number 7. Prove that the binary operation of addition is in C is associative, commutative, possess identity element, and is such that every element of C has additive inverse. If C is a complex number, we have to prove three property associative law. If we have three complex number, a plus iota b, c plus iota d, c plus iota d, and e plus iota f. First property, associative law. A plus iota b, associative law of addition. A plus iota b plus c plus
C plus
iota d plus e plus iota f is equal to a plus iota b, c plus iota d plus e plus iota f. Associative law mean if we add a plus b and then c is equal to plus c plus d, and after that plus a. z1 plus z2, first add z1 plus z2, then z3, or first plus z2 plus z3, then z1. Answer will be same. This is called associative law. And commutative law, z1 plus z2 is equal to z2 plus z1.
Z.
The first part, this is first and then second. If we have two numbers, two complex number, z1 and z2, z1 plus z2 is equal to z2 plus
Z1.
z1. Commutative law is also applicable. Third law is additive inverse, and 0 is the identity element for addition in C. What is identity elements? z1 plus 0 is equal to 0 plus z1 is equal to z1, then 0 is called additive identity. 0 is called additive identity. And every element of C has additive inverse. 0 is also called additive inverse. Not multiplicative inverse. Additive inverse means if we add 0 in Z1 or Z1 in 0, result will be same complex number. And article number 8, prove that the product of two complex numbers is a complex number. Article 8, if we product two complex number, our result will also be a complex number. If Z1 is equal to A plus iota B and Z2 is equal to C plus iota D, then Z1 is equal to Z1 multiplied by Z2 multiplied by Z2 is equal to any complex number. Result will be complex number. Article number 9. Prove that the binary operation of multiplication in C is associative, commutative, possess unique identity element. In Article 7, we show the additive properties. Now we will show multiplicative property, associative, commutative, and identity element. We have three. If we have three complex numbers Z1, Z2, Z3, then what do you mean by associative property? Z1 multiply by Z2 and then multiply by Z3 is equal to Z1 multiply by Z2 multiply by Z3. This is called associative property. And commutative property,
Z1 into
Z2 is equal to
Z2 into Z1.
Z1 into Z2 is equal to Z2 into Z3. And third is identity element or identity inverse. Any complex number Z1 is multiplied by 1 is multiplied by Z1, our answer is Z1, therefore 1 is identity element. Element, or we can say additive inverse, multiplicative inverse. 1 is also multiplicative inverse, a complex number. And 1 is unique element. You have any number which is multiplied by complex number, you will get same complex number other than 1. You have any number other than 1 which is multiplied by any complex number, you get same complex number.
Yes.
Yes. Which number? Our answer will be Z1. Right or wrong? Is it possible? Not possible. So 1 is
Not
unique.
possible.
Only 1 is an identity element. Article number 10. Conjugate of a complex number. If Z is equal to A plus iota B, then conjugate of Z is equal to
A minus iota B.
of Z, that is Z bar is equal to A minus iota B. Modulus of a complex number. If we have Z is equal to A plus iota B, any complex number, then modulus of Z is represented by this symbol is equal to A square plus B square. This is called modulus of a complex number. It is also called absolute value of Z. Also called absolute value of Z. And if we product a complex number with its conjugate, then our answer will be modulus of complex numbers here, which is always a real number, non-negative real number. If we product a complex number with its conjugate, our result is square of modulus, and which is a non-negative real number. Non-negative mean positive value and real value.
Okay.
Non-negative real number. Article number 11, prove that modulus of Z is equal to 0 if and only if Z is equal to 0. Article 11, modulus of Z is 0. When modulus of Z is 0, then complex number is 0. And only if Z is equal
That
to
is equal to 0.
0. For example, Z is equal to 0 plus iota 0. Modulus of Z a square plus
Plus B square.
b square is equal to 0. A square plus b square is equal to 0. So if a complex number is 0, then its modulus is also 0. An inverse of a complex number, article number 12. Inverse of a complex number. We have Z a complex number, then 1 over Z inverse of Z is 1 over Z, or we can write Z power minus 1.
Minus 1.
First, if we multiply Z by its inverse, then it is also always equal to 1. If complex number is multiplied by its inverse, our result will always be 1. Now some results. Article 13. First result, Z1 plus Z2 conjugate is equal to conjugate of Z1 plus
Plus conjugate of Z2.
Z2. Second result, Z1 multiplied by Z2 conjugate is equal to Z1 conjugate multiplied by Z2.
Z2 conjugate.
Number 3, Z1 over Z2
Conjugate.
is equal to
Z1 conjugate over Z2 conjugate.
Z1 conjugate over
Z2 conjugate.
Z. Four, modulus of Z is equal to
Modulus of Z
Modulus of
conjugate.
Z conjugate. Number 5, Z1 multiplied by Z2 modulus is equal to Z1 modulus into
dot Z2
Z2
modulus.
modulus. And number 6, Z1 over Z2 modulus is equal to Z1 modulus over
Z2.
Z2 modulus. Now article number 14. If Z1 and Z2 are any two complex number, prove that Z1 plus Z2 modulus Z1 plus Z2 modulus square whole square plus Z1 minus Z2 modulus whole square is always equal to double of modulus Z1 square plus
Z2.
Z2 square. This is the result of article number 14. We take modulus of two complex number. Now article number 15. If Z1 and Z2 are two complex number, prove that Z1 plus Z2
Z2.
modulus is always less than or equal to Z1 modulus plus Z2 modulus. And the above result can be extended to n complex number. Corollary: Z1 plus Z2 plus Z3 so on Zn modulus is less than or equal to Z1 modulus, Z2 modulus, Z3 modulus, so on Zn modulus. Okay, these are results which we will use in questions. Now see example number 5. Find real theta such that 3 plus 2 iota sine theta 1 minus 2 iota sine theta is purely real. Example number 5. Z is equal to, let Z is equal to 3 plus 2 iota sine theta over 1 minus 2 iota sine theta. Now we will rationalize it.
1 plus 2 iota sine theta.
1 plus 2 iota sine theta over 1 plus 2 iota sine theta is equal to 3 multiply 1 3 3 to 6 6 iota
Sine theta.
sine theta plus 2 iota
Sine theta.
theta plus 2 to 4 iota square sine square theta over a minus b a plus b a square minus b
Square.
square, which is equal to 3 plus 8 iota sine theta iota square minus 1 minus 4
4
sine
sine
square
square theta.
theta over 1 minus 2 to 4 iota square minus 1 plus 4
Sine theta.
sine square theta. which is equal to separate real and imaginary part 3 minus 4
4 sine square theta
sine square theta plus iota 8
8 sine theta
sine theta over 1 plus
plus
4
4 sine square theta.
sine square theta. We can write it as, we want to separate 1 plus 4
Theta.
square theta over 1 plus 4
1 plus 4 sine square theta.
sine square theta. Since z is purely real, since z is purely
Real.
Real.
real, when it will be purely real, when imaginary part is 0, therefore imaginary part value of b will be 0. Therefore 8 sine theta over 1 plus 4 sine square theta is equal to 0, or 8 sine theta is equal to 0. Sine theta is equal to 0. Theta is equal to n pi, general value of theta. N pi where n belongs to integers. Okay. This is general value. Sine theta is equal to 0 and theta is equal to 9 theta. We do it in trigonometry chapter. Example number 6. Find the multiplicative inverse of 2 minus 3 iota. Example number 6. We have a complex number z is equal to 2 minus 3 iota.
Theta.
Now its multiplicative inverse is 1 over z.
Z.
1 over 2
2
minus 3
3
iota. Multiply by
2 plus 3
plus 3 iota over 2 plus 3 iota. 2 plus 3 iota over 2a square minus
minus 3 iota square.
b square is equal to 2 plus 3 iota over 2 to 4, 3, 9 iota square minus 1 plus 9.
Plus 9.
2 plus 3 iota over 13,
13.
or 2 over 13 plus 3 over 13. This is multiplicative inverse of given complex number. Take screenshot.
Done, sir.
Take again.
Done.
Take again.
Done.
Take again.
Done.
Again.
Done.
Take screenshot.
Done, sir.
Again.
Done.
Now example number 7, find the conjugate of given complex number. Example number 7, we have a complex number z is equal to 3 minus 2 iota 2 plus 3 iota over 1 plus 2 iota multiply by 2 minus iota. We can write its conjugate without solving it. Hello?
Hello.
We can write its conjugate.
Wait.
Yes or no?
Yes.
Right. How we can write its conjugate? Tell me. Speak conjugate of z.
3 conjugate.
Hello.
Hello.
Speak its conjugate. Yusik, I can write. Now write its conjugate.
3,
We
6.
cannot write its conjugate. First, we will solve it as a complex number. We will convert it in complex number. Multiply 3 to 6. 3, 3, 9. Minus 4 iota minus 6 iota square. Over 2 minus iota plus 4 iota minus 2 iota square, which is equal to 6 plus 5 iota plus 6 over 2 plus 3 iota plus 2. 6 plus 6, 12 plus
5 iota.
5 iota, 4 plus
3
3
iota.
iota. Now rationalize it. 4 minus
4 minus 3 iota
over 4
over 4
minus,
minus 3 iota.
which is equal to 48 minus 36 iota plus 20 iota minus 15 iota square over a square minus
E square.
square is equal to 48 plus 15 iota square plus iota square minus 1 minus minus plus 15 and minus 16 iota over 4 into 4 16 minus 9 iota square is equal to a plus 5 13 4 plus 1 5 plus 1 6 63 minus 16 iota over 6
25.
plus 9
16
63
plus 9.
63 minus 16 iota over 25 over 25.
25.
Now this is complex number form. We can write its conjugate. Then conjugate of z is equal to 63 over 25 plus 16 over 25. Now take screenshot.
Done, sir.